Thank you for inviting me to give this talk at this wonderful summer school in this wonderful area as well. So it was very nice to wake up this morning to the sound of chirping birds instead of traffic, which is what I usually wake up to. So just a little bit about me. So my name's Catherine. I'm currently a lecturer at the University of Leeds, and I lead a small team that works mainly on astrochemistry, but we do everything from molecular clouds all the way to the atmospheres of forming and exoplanets, so planets around other stars. So what I thought I would talk to you today about, so I was given a title, Organic Chemistry in Solar Systems. So I'm going to give you a little bit of a background into astrochemistry, because I know a lot of you work in astrobiology. So I'm going to kind of make that link between the ingredients that we have in the interstellar medium with kind of those building blocks of those prebiotic molecules that you might be studying. And I'm going to give you an observational perspective on what we're actually learning about the organic composition of these disks that form around young stars. So I think it's good to start and just remind ourselves of kind of the big questions that we're trying to answer in our field. And those are we unique? So is our solar system particularly unique in its composition of its planets and architecture of its planets as well, and its other planetary objects like asteroids and comets? And is our solar system the only place where a planet could possibly have begun life? Another big question is, where do we come from? What are our origins? Where do they start? Do they start all the way back in the molecular cloud from which the sun formed? And I'll talk a little bit about that. I know finally what we want to know is, are we alone? Are we the only, again, sentient civilization that has managed to arise in the universe? And ultimately, we want to understand if what happened on Earth is actually possible to happen elsewhere. And part of that question is what you've already been discussing, which is what sets the habitability of planets. So let's kind of start a little bit back in the beginning and let us think about where we come from and are we unique. And when we think of the interstellar medium, which is a space between the stars, we look at the night sky, you see pinpricks of light that are the stars, and in between the stars it looks very dark. It's almost as if there's nothing there. But actually the interstellar medium is a really vibrant and very complex medium. So this is a really nice image taken as kind of a multicolor image taken with optical and near infrared imaging. And this is of the Carina Nebula. So you see Eta Carina, the massive star that's dying in the bottom left of the image here. You see a stellar cluster that is formed in the center. That's booming in UV radiation that's illuminating and blowing out a bubble around it. And then what you see in the right hand of the picture here, kind of dark regions that are sitting in front of this nebula. And it's these dark regions that are the most interesting actually for star formation. So these dark regions are large clouds of dust and gas, which are attenuating the light coming from this very bright stellar cluster nearby. And it's within these dark regions that the next generation of stars will form. So the interstellar medium is really kind of a star formation factory. So here we have a nice image of the Milky Way. Again, you can see why we get the name of the Milky Way. This is an optical light image. So you see the kind of diffuse milky light coming from the stars in the Milky Way. And you see here also the kind of lane of dust and gas that's obscuring the light coming from the stars. And within these dense clouds that you also saw in that image of the Carina Nebula, these dense clouds, once they cool enough such that thermal pressure can no longer support against gravity, they can collapse to form either a single star or a cluster of stars. Those stars will burn their hydrogen for a certain period of time, dependent on their mass, and especially the high mass stars. They will go boom, explode as supernova, and they will generate these very strong shocks and kind of create feedback and inject energy into the surrounding interstellar medium, and also inject new elements into the interstellar medium as well. So you can think about the interstellar medium of galaxies as kind of being this life cycle of dust and gas. So we get stars forming, those stars die, and they inject dust and elements back into the interstellar medium to kind of seed the next generation of stars. And this life cycle is very important for us. You know, if we're thinking about life and the origins of life, we can also think about the origins of elements, and actually the elements that make up us. And this is a really nice view of the periodic table. So you usually see this in a very different format. And this is the origins of the solar system elements, colorized by the origins of the elements themselves. So again, those processes that actually led to the formation of key elements. So you see here in green we have elements formed during the Big Bang, so Big Bang fusion. So there's a very light elements like hydrogen, helium, and also a bit of lithium. In yellow we have dying low mass stars, so stars just like the sun when they die. Here we have exploding massive stars in orange, and I can't quite read this. In purple we have cosmic ray fusion. In the darker purple we have merging neutron stars. So you know about these, hopefully, if you've been watching the news about gravitational waves. These are the most energetic events that can happen in space, and it's these merging neutron stars that create these very heavy elements that you see here. And then finally in blue we have exploding white dwarfs. And you can see that in orange and blue is kind of mainly these key elements that make up us, that make up life. So if we look here, we are 1% by mass made up out of exploding white dwarfs. We are 9.5% by mass made up out of these light elements, hydrogen and helium, etc. We are 16.5% dying low mass stars, just like the sun. And the vast majority of elements that we are made up out of, I've clicked a little too far, 73% here, is made up out of exploding massive stars. So those stars that are so massive that at the end of their lives they explode as supernova. And these exploding massive stars are very important for key elements like carbon, nitrogen, oxygen, phosphorus, and sulfur. So how do we then go from these key elements that are formed through this life cycle of stars to actually life itself? Because that's one end of the spectrum too, which is very complicated, a series of steps. And, you know, thinking about this as an astrochemist really more than an astrobiologist, so most of you are going to be experts in this more than I am. But if we look at a cell, what is it that a cell needs to be alive, so to speak? We need a semi-permeable membrane. We need an energy gradient we can exploit as an energy source. We need an information carrier such as RNA or DNA. As an astrochemist, if we want to sense life in another environment, especially outside of the solar system, these are very difficult things for us to look for. But I suppose if you look at the structures that create a cell, then these are proteins, lipids, and other macromolecular structures. And it is these things that perhaps, so those building blocks that we need for building cells are perhaps the things that we can go and try to remotely sense using astrophysical observations. And, you know, the building block of, for example, proteins or amino acids, such as you see here. And again, amino acids are not so complex a molecule, as you can see here. So if you replace this R group here with a hydrogen, then you get the simplest amino acid, glycine. Again, glycine is probably going to be a molecule that's very difficult for us to see, especially through remote sensing. So what we do as astrochemists is we try to look for molecules that share functional groups with these key building blocks. So we might look for molecules that have an amine group, such as the NH2 group here, or molecules that have the carboxylic acid group, the COOH group here. And of course we also look for hydrocarbon molecules as well, really to see if we have those feedstock functional groups available to form things like amino acids that we know are the monomers of proteins. So we're kind of thinking about like down this end of the chain, how we go from elements to those functional organic groups with some steps in between to actually get to something that looks like life. So kind of the next little bit of the talk, I'm going to talk about are the building blocks of life made in space. So by building blocks, I'm talking about those organic molecules that share functional groups with things like amino acids. And the first part of answering this question is actually to ask ourselves, how do we even see molecules in space? So we do this by exploiting the fact that molecules have very distinct rotational and vibrational spectra. So that means that they have quite low-lying energy transitions that emit radiation at quite low frequencies or long wavelengths. And that allows us to exploit observational facilities that operate all the way from centimetre wavelengths to around sub-millimetre wavelengths. Or if you prefer frequency, that would be like tens of gigahertz to around a terahertz or so. And there's quite a few different observatories that we use to do this. So you see here the electromagnetic spectrum. So we're going from the radio on the left all the way to the ultraviolet on the right. And you see here the little optical window here, visible light at around 10 to the 15 hertz, or a few hundred nanometers. And then superimposed on this, you see the transmission of the Earth's atmosphere. So up here we are opaque to light at this particular wavelength or frequency, and where you see kind of the dips is where the atmosphere is transparent. So you can see that we can do a lot of optical spectroscopy from the ground, because of course we see the world in visible light. So that visible light is able to reach the surface of the Earth. But there's a lot of windows here where actually our atmosphere is opaque to the penetration of light at that wavelength. So over here at radio wavelengths, we're also transparent, and a lot of astrochemistry and detection of molecules is actually done with big single dish telescopes, such as the 100-meter GPT over here, which is in Virginia in the US. And as we increase in frequency or go to shorter wavelengths, so now we're in the microwave region, we start to see here the atmosphere becomes generally more opaque. And in these wavelength regions, we move to sub-millimeter or millimeter wave antenna, such as ALMA and NOEMA, that we put at altitude to get above as much of the Earth's atmosphere as possible. We also try, ALMA is also in the Atacama Desert in Chile, where it's very dry, and that also really helps us to kind of see through the atmosphere, because water is a very good absorber of radiation. So we do a lot of the grunt work at millimeter and sub-millimeter wavelengths is now done with these large interferometric arrays such as ALMA and NOEMA. And then we have this region here at far infrared wavelengths where our atmosphere is actually completely opaque. And that's because we're emitting far infrared radiation. So our temperature of the Earth is 300 Kelvin. And if you work out using Wien's law, the peak in the black body spectrum of a 300 Kelvin black body, then it's about far infrared wavelengths. So then we have to go to space, and a very important mission that we had in kind of the 2000s was the Herschel mission, which was one of the keystone missions of ESA back then. And that did a lot of work looking at far infrared lines, especially small hydrides and molecules like water. And now towards the near and mid-infrared, we have JWST. This is our next kind of big infrared mission, and you will start to see, hopefully, some of the results from that mission on disks and forming stars coming out in the next few months. So we exploit these gaps in the electromagnetic spectrum to look for molecules from the ground. At mid-infrared and far infrared wavelengths, we need to do that from space, so it's a bit trickier. So how do we then use and see molecules in space? So each molecule has a unique spectral fingerprint, and that's because when we look at their rotational transitions, that's related to the moment of inertia of the rotating body, if we look at the classical case. And because molecules are identified by the unique combination of atoms that make them up, they all have different moments of inertia and different rotational constants about their principal axes of rotation. And this leads to each molecule, as it's uniquely identified, having a unique spectrum. So if you know the spectral lines to look for, you can actually uniquely identify a molecule in space. You can think about it as having a spectral fingerprint. And just to kind of illustrate that for you, this is a little snapshot of a synthetic spectrum of formamide, so NH2, CHO. Here we have our amine group, so one of those groups that we're interested to look for. And this is a little snapshot of the spectrum at around 300 gigahertz or 1 millimeter. And you can see that formamide has all of these very distinct, very well separated, in most cases, spectral lines. And if we take another molecule that's not super different, not too far off the same mass, but this time instead of a formyl group, we have a methyl group. So this is methylamine, CH3NH2. Again, having this important amine group that we're interested in looking for. This is formamide and this is methylamine. And you can see that these look very different. So they're going to rotate in space with different moments of inertia. around their principal rotational axes. So if I overlay the spectrum for methylamine, you can see that you have very strong lines that are sitting at very distinct frequencies away from those strong lines of formamide. So if you have a very high resolution spectrometer, you can very, very accurately tune your spectrometer to pick up lines only from these particular species. And that allows us to then uniquely actually identify these molecules through remote sensing. And just to show you kind of the power of Herschel, I really like this image here. So we don't have a far infrared observatory at the moment. We've lost Herschel because that had a finite lifetime. It ran out of coolant and then it couldn't be cooled to the temperatures that we needed to use it at anymore. We had Sophia, which was the stratospheric space observatory. That was the telescope mounted on a Boeing 747 run by NASA. That's now been decommissioned. So we have this kind of gap in the electromagnetic spectrum that we have to think about as a community about how we fill in the coming years. But this is a really nice unbiased line spectra taken towards Orion, the Orion molecular cloud, which is our nearest kind of high and low mass star forming region. And you can see here, this is really booming in molecular lines. And you have lines from very simple molecules, such as water here, sulfur dioxide, here's another water line. But even in these far infrared wavelengths, we can pick up molecules from more organic, of a more organic nature, such as methanol, simple alcohol, acrylonitrile, simple nitrile, methyl formate as well. So even in just this little snapshot of a far infrared spectrum towards a nearby star-forming cloud, we see a huge number of these very strong line transitions indicative of being many, many different molecules present in this star-forming region. So how do we then make all of these molecules? Well, if we look at, and we're really talking about volatile molecules here as well, if we look at the ingredients that we have available for doing chemistry and converting elements into molecules in space, then this is another version of the periodic table. This is kind of the astronomers or astrochemists periodic table, because not every element in space will go through chemistry and form a molecule, at least not a volatile molecule. So here we have the sizes of the boxes are scaled to the amount of mass we have available of that element. So you can see we have most of what we have available for forming molecules in space is hydrogen, and we have about 10% of helium, and then we have about 0.1% of a lot of other things such as carbon, nitrogen, oxygen, sulfur. We can also make molecules with some of the inert gases as well. So we actually see argon H+ in space, and then we have some of the metals here such as sodium, magnesium, aluminium, silicon, etc. So we don't have a lot to work with if you look at this, but because we can combine, especially using the carbon backbone, these elements in lots of different ways, you actually see a very unique and quite exotic chemistry that can happen in space. And if I give you a little bit of a historical perspective here, this is the year of detection on the x-axis, and this is the cumulative number of detected molecules on the y-axis. And you can see that really astrochemistry started back here in the 1940s and 1960s. The first molecules in space were detected serendipitously using optical absorption spectra. So people were looking for atoms in the diffuse interstellar medium and actually picked up lines from simple molecules like CN and OH. And then nothing much happened until the 1960s, where we actually had the advent of kind of radio astronomy, where we took antennae that were developed for military use essentially and started pointing them towards the sky and replacing the back end with spectrometers. And then we really had the explosion of detections. So you see here the NRAO 36-foot telescope really did a lot of work back in the 60s. You can see here the ERAM 30-meter telescope coming online in 1984, and that has been the most successful telescope to date in detecting new molecules in space. We see the GBT coming online in 2001, and then we see things like ALMA as well. And at this point in time, 2020, we had detected 240 unique molecules in space. But actually, if I were to extrapolate this to 2023, I think we have at least 30 or 40 more. It's really almost like an exponential increase in what we're detecting now. So we don't have a lot to work with, but we do detect and see a lot of different molecules. So how exactly? And this is a little kind of snapshot of astrochemistry. If you have any questions about this, please come and ask me later, because I'm going to move on a little bit more to talk about disks in a little bit. So what's our understanding of the chemistry that actually happens in this environment? Well, as you can imagine, space is a really harsh environment. You have clusters of stars, you have bright stars that are booming out UV, you have cosmic rays, and all of this radiation acts to destroy molecules. So you take two atoms, you manage to put them together in a bond, very soon a UV photon might hit that molecule and split them apart. So it's actually pretty difficult to make molecules through two-body collisions. Gas phase chemical rates are slow because they rely on those collisions to form, and particular chemical processes such as radiative association, which is where the bond stabilizes by emitting a photon. These are slow. It takes a lot of time to actually take elements and form them into molecules. And if you want particularly complex molecules, so again, those building blocks that we're talking about for prebiotic chemistry, so we take one of the largest molecules we've seen uniquely in space, ethylene glycol. We need to take 10 atoms and make 9 bonds. Now, on Earth, that's really easy, but in space, it's really hard because you need two-body collisions in order to form each of these individual bonds. So there's a huge series of reactions that you would need to go through to actually get to something as complex as ethylene glycol. But part of the answer to the puzzle of this is actually that a lot of chemistry, especially for our large organic molecules in space, doesn't necessarily happen in the gas phase. And this comes back also to that life cycle of dust and gas that I talked about at the very start. So one of the things that stars do when they come to the end of their lives is in their surroundings, they create just the right conditions to fuse elements into dust grains. And those dust grains would be things like silicates, exactly the same stuff that the Earth is essentially made out of. And you see here kind of a beautiful nebula of this dying star blowing out its envelope, in which it is also producing dust grains as well. And these little dust grains look a little bit like this. So they're little fluffy kind of aggregates. They're not kind of compact spheres. What these dust grains can do if they make their way into the interstellar medium and into a molecular cloud, which is quite cold, then they can form ices on the surfaces of themselves. So this is literally where oxygen atoms or carbon or nitrogen atoms can stick to these dust grains. We've got a lot of free hydrogen roaming about. They hydrogenate those molecules, and that's exactly how we build water ices in interstellar space. And why does this help actually enhance chemical complexity? Well, you get these molecular ices forming, they grow on these cold dust grains. That creates a meeting place for chemical reactions. So no longer are you reliant on things meeting serendipitously through collisions in the gas phase. You're actually bringing a lot of raw material into one place, onto these surfaces, and that just helps to enhance the likelihood of a reaction taking place. And the other really, important thing, this is a whole area of chemistry called heterogeneous catalysis. So loads of physical chemists work on this. This is where you have surface reactions enabling bond formation. So bond formation is actually when taking two things together and making a bond is a highly exothermic process, usually. And if you don't have any way to stabilize that bond, then the two reactants will just fly apart because there's so much energy in that interaction. So what the surface does, the surface actually absorbs that excess energy and allows that bond to form. So then it becomes not so difficult to build something like ethylene glycol. All you need is for the atoms to meet, for the reaction to happen, and those bonds to be stabilized. And then the final thing that's really important, I think, which I'll come on to when I talk more about disks and planet formation, is these molecules then become kind of protected in the ice. They're not floating around in interstellar space to be dissociated by that energetic radiation. They're really sitting in kind of a nice little cocoon on these dust grains. They may be subject to some processing, but certainly their survival rate would be higher than if they were in the gas phase. And I have a nice little video here kind of showing you some of these concepts that I've just talked about. So what you're going to see here, in the background we have a water ice surface, and then in the foreground you're going to see CO molecules arriving on that surface and different types of chemical processes happening. There we go. So we have a water ice surface here, we have a CO molecule getting hydrogenated. The free hydrogens are very light, so they can move and scan across the surface. And by hydrogenating the CO, you can very quickly make methanol and formaldehyde. So we have this little methanol molecule formed here. So if we look at these two CO molecules here side by side, one gets hydrogenated to make formaldehyde, the other one gets hydrogenated to form HCO, and these two things are radicals, so they will react and form a new molecule, methyl formate. Here we have a CO molecule arriving. We have one over here that gets a little bit of energy, so it translates across the surface. These form glyoxyl by associating, and that can also be hydrogenated to form another bigger molecule like glycolaldehyde. So we have methanol, methyl formate, glycolaldehyde formed just from two ingredients, CO and hydrogen. Here we have another CO molecule hydrogenated. We have a photon will come in here. It will pop off a hydrogen, make two radicals that are sitting side by side, which again want to be together. They don't want to be radicals, so they form another methyl formate. So in this way, and it doesn't happen on these time scales, right? It happens on millions of years. But we just had two ingredients there. We had a water ice surface to mediate the reaction. We have CO that's arriving on the ice surface, and that will happen if the temperature is below about 20 Kelvin. And we have free hydrogen, which is created in space by cosmic ionization of H2. And with only those two ingredients, you could see how we could very readily form three larger molecules, methyl, methyl formate, and glycolaldehyde. And to do this in the gas phase is really, really difficult. But we know from lab experiments that these mechanisms work, and they work even at very, very low temperatures. Okay. So moving on a little bit, right, so that's all very well and good. You know, the interstellar medium is not a chemically, inert place. We have a lot of chemistry happening, and we can form actually really big molecules in space as well. Why does this matter actually for the origin of life? Well, you would have heard about this from, I think, Manuel's talks also on Monday. But it matters because we form, our sun, planetary system and everything forms within these interstellar clouds where all this chemistry is happening. So here we have a cloud that's collapsing. It's collapsing, conserving angular momentum. So what the system does is it spreads out to form a disk. In order to conserve angular momentum, it creates jets, which allows the star to stabilize as well. And this swirling disk of dust and gas that originated from the cloud. This is stuff that's been left over from that star formation. It's within this orbiting disk that we form our planetary systems. And this is exactly how we think the solar system formed as well. There's nothing yet to indicate that we formed any different from the way that we see other stars forming. Okay. So we're left with, as you can see at the end of this video, we have this disk of dust and gas within which we have forming planets. So I like this little quote by Carl Sagan. I don't know if you've heard this before. So we are made of star stuff. It's quite a famous quote. And that was from his TV show he did back, I think it was in the 1970s or early 80s. I think you can get it all on YouTube if you're interested. So he said, we are made of star stuff. And he was alluding to the fact, exactly what I said at the start, that when stars die, they blow out and create all those elements that we need for the structures of life to exist. So that's carbon, oxygen, nitrogen, phosphorus, etc. But I would say that there's another kind of step to us existing, and that's the fact that those elements make their way into molecules. And chemistry happens in space. Because the first stars would have been only massive stars. You would not have had a low-mass star forming in the early universe. And the reason for that is because in order to form a low-mass star, you really need the cloud to be able to make molecules like carbon monoxide, which allow the cloud to cool by emitting radiation in order to reduce the thermal pressure enough for that cloud of that mass to collapse to form a low-mass star. So we needed carbon and oxygen to exist, but we also needed chemistry to form carbon monoxide in order for low-mass stars to form. So there's another step, I think, and this is where astrochemistry is really important. The formation of those molecules is really what allowed then low-mass stars to form, is what I'm saying. Okay, so this is the little video that I just showed you in a more schematic form. We have dying stars seeding the diffuse interstellar medium. We have condensations forming, denser regions forming in the interstellar medium, which cool through CO emission, usually allowing gravity to win over thermal pressure, and that collapses, conserving angular momentum to form an accretion disk around the young sun. And again, this is where planetary systems will form within this accretion disk. So for the next kind of bit of the talk, I'm going to focus mainly on this object here, which in this schematic is called an accretion disk, but is actually what we would call in my field a protoplanetary disk or a planet-forming disk. So a disk around a young star that will form a planetary system, essentially. And there's lots of different reasons why we want to study these particular objects. So we want to know the initial conditions of solar system formation. So planets are going to form within these objects. So we want to understand what the structure, physical and chemical structure of these objects. We want to understand how planets form. That's still an open question, believe it or not, that we have been studying for decades. We want to understand the architecture of exoplanetary systems. So we know one thing, and that our solar system seems to be unique in the fact that we don't have what's called a super Earth, which are the most common exoplanets actually detected to date. So are we unique in that, or are there biases, I suppose, perhaps still in our detection techniques? We want to understand the origin of complexity in solar systems, again feeding into origin of life and our origins as well. So we studied these objects for a whole host of regions, both to just understand generally how planets form, but also to understand origins and our origins specifically. So we're now going to zoom in a little bit, and for the next bit of the talk, I'm going to focus on protoplanetary disks, both what we currently understand about the physics and chemistry going on in these disks, and then I'll move on to talk more about what we're seeing, especially the organic molecules and like chemical structures we're seeing in these objects. So this is my little cartoon of the chemical structure of a protoplanetary disk. So the first thing to point out is, just like the molecular clouds we were talking about, we have two phases of molecules or volatiles in disks. We have the gas, which is mainly molecular hydrogen, and we have the ice, which is mainly water ice. So water is the most abundant molecule in space after H2. It's not in gas phase form, it's mainly in ice form. And if we look at a disk, so this is a little snapshot of a disk, you'll see it's not geometrically thin, it has vertical extent, and that's because the disks are probably sitting close to hydrostatic equilibrium, just like our atmosphere on the Earth. This is what we call the disk midplane, so we're taking kind of a slice through the disk, and this is a star, which is pumping out UV. Young stars are bright in X-rays as well, and also energetic particles in the form of a stellar wind. And the coldest, densest region of the disk is what we call this frozen midplane, and this is where most heavy molecules are going to be frozen out as ices on the dust grains. Then as we move upwards towards what we call the disk surface or disk atmosphere, this is a bit warmer, maybe around 30 to 50 Kelvin, because it's being warmed and irradiated by the star. And this is what we call the warm molecular layer of the disk. And as we go towards the surface, this is the bit of the disk that's most irradiated by the central star, but also the interstellar medium as well. And this surface can be very abundant in atoms and ions, which have been dissociated and ionized by the energetic radiation. So when we turn our telescopes to a nearby protoplanetary disk, then what we're really looking at is kind of this kind of molecular layer or disk atmosphere here. And we can probe this region using multi-wavelength observations. So if we want to see very close to the star, we can use near-infrared observations, which typically probe material at around thousands of Kelvin. So that would be, we can do that from the ground using high-resolution near-infrared spectroscopy on the VLT, for example. If we want to see kind of starting to get within the kind of the planet-forming region, so within about 10 astronomical units, then we can do that at mid-infrared wavelengths. That's probing material, it's around a few hundred Kelvin, mainly vibrational transitions of molecules like CO, CO2, water, etc. But the vast majority of these disks, and these disks can be quite large, they can go out to a few hundred astronomical units. So if we think about the size of the solar system being roughly out to the orbit of Neptune, these disks are probably 3, 4, if not 5 times bigger than that. This material is cold. and doesn't emit at near to mid-infrareds. It only emits actually at sub-millimeter wavelengths, which is material that's typically of the order of a few tens of kelvins in temperature. And this temperature gradient is really set just by the proximity of the material in the disk to the star, which is the main heating mechanism. So if we want to really probe the structure of disks, especially kind of beyond the planet forming region, then we really need to go to sub-millimeter wavelengths to do that. So what kind of chemical structures are we interested in looking for? Well, if we're thinking about how planets and especially also comets are built within a disk, then one of the most important structures is kind of the positions of snow lines. So because we have this temperature gradient where the inner region of the disk is very hot and it's going so a few thousands of Kelvin down to tens of Kelvin at 100 astronomical units, for example, you have this temperature gradient in what we call the midplane of the disk, where all of this action is really happening. And at some temperature threshold, water, for example, is no longer going to be able to exist in the gas phase and will freeze out as ice on the dust grains. So, for example, in a disk, you might have the water snow line occurring at about 150 Kelvin. As you move further out, you freeze out then CO2 as well at about 70 Kelvin. And moving further out, when you reach about 20 Kelvin, you'll also deplete CO from the gas phase onto the ice as well. And this is really important. The snow lines are very important to consider because it's really these different compositional transitions or gradients that will determine the ingredients or compositions of the planetesimals and comets that you're forming there. And the exoplanet community is very interested in these as well because the relative ratios of dominant volatiles, such as water, CO, CO2, will dictate the resulting compositions of planetary atmospheres. So a planet that forms out here, perhaps, which is heavily depleted in the gas from water, CO2 and CO, will be very metal poor in its atmosphere if it's accreting its atmosphere mainly from the gas in the disk, because there will really only be hydrogen available. Whereas a planet forming within the snow line will have all of these volatiles available to be accreted onto the atmosphere. So these snow lines are actually really important in dictating those compositional, the composition of atmospheres of planets, but also of the comets that you build from those ices that have frozen out as well. And just to point out here, you know, these snow lines can be modified to some extent by chemistry. So it's not that you freeze in the composition from the gas. You have cosmic rays, interstellar UV radiation, and to some extent X-rays as well, can actually penetrate through to this icy zone and also do some chemistry, as I'll talk about a little bit. So we have a lot of chemistry happening in the disk, so creating those vertical stratification and the radial stratification in snow lines. But the dust is doing a lot in the disk as well, and this is kind of, you know, the first steps if you think about planet formation, because planets form from the solid material in the disk, not the gas in the disk. So the dust grains are doing a lot at the same time that the chemistry is happening. So once dust grains grow in the outer disk to a size that they are no longer well coupled with the gas, then they feel the gravity of the midplane and they settle down towards the midplane. And here, because they're not well coupled with the gas, they actually feel a headwind and a drag force, because they're trying to move at Keplerian velocities, but the gas feels its own gas pressure, so it's slightly slower, and that creates a drag force. So these dust grains actually settle in the outer disk and drift inwards. And at around the positions of snow lines, we also tend to see that those dust grains can actually grow more effectively as well. So we have dust settling, we have dust drift, and we also have dust growth. So in a protoplanetary disk, the dust doesn't have the same size properties or dust to gas mass ratios as you have in the interstellar cloud. There's a lot going on that's condensing and concentrating the dust. And then if you have a planet that's embedded, if you have a planet that is able to form at some point in the disk, then that can actually create what we call little dust traps. So the planet creates, basically, it's sweeping up the material in its vicinity, it's removing angular momentum from the disk, it creates a cavity in the gas that then creates a little pressure trap, external and usually internal to it as well. And that traps dust grains in rings, essentially, and I'll show you some images of that as well. So if we have planets already forming in the disk, there's a feedback on the dust distribution and then also on the chemistry as well. And remember that I told you that complex organic molecules form on, we think, on ices in the interstellar medium. Well, if you start to modify your dust distribution in the disk, you're also going to modify a lot of the chemistry that's happening on those icy dust grains as well. So, you know, although the ices are sitting in the midplane, they're not necessarily chemically inert. You have processing by UV, X-rays and cosmic rays that may change the composition of your ices. You can get mixing in both the radial and vertical directions, so mixing up from the disk midplane to the atmosphere, and you can get mixing towards the inner hotter region of the disk and outwards as well. So you can get a lot of reprocessing of your material, especially your icy material that is present on your ice grains. So we think, and this is kind of my area of research, if you like, we really look at what types of chemistry can happen on these icy dust grains in disks to try to understand how that material is processed by being present in the disk. So a lot going on, quite complex physics coupled with chemistry. So let's now take a little look at what we've actually seen in protoplanetary disks. So moving on a little bit more to the observational perspective. So this is a little kind of rainbow of molecules we've detected in interstellar space to date. There's a really nice review by Brett McGuire if you're interested in this. I can give you the reference if you want. So this is what we've seen in interstellar space. Remember I said by 2020 it was 240 molecules. It's now probably more like 270. And we go from everything that's small diatomic molecules like H2 up to these large, what would be considered very complex organic molecules, including the largest molecules ever uniquely identified in space, the Buckminster fullerene C60 and C70. And if I overlay what we've detected in disks so far, so disks are difficult to observe. They are small objects and they're far away. So if we take a disk or a young star that hosts a disk that's at 100 parsecs away from us, and that disk is 50 AU, so 50 astronomical units, then that disk will only be 1 arc second in diameter on the sky. And that's really tiny if we think about our field of view of most of our, especially single dish telescopes. So it's a really tiny object that's got very compact emission. So it's harder to detect molecules in those compact objects than it is in kind of bigger molecular clouds and protostellar envelopes. But nevertheless, the ones that you see here ringed are the ones that we've uniquely detected. So we see a lot of those simple molecules that we're interested in. So things like CO and water. We see cations like N2H plus and HCO plus as well that allow us to measure ionization. So that's here. And we're starting to see hydrocarbons like C3H2, so cyclopropionylidene, formic acid, and you can see that we're starting to reach up into these larger organic molecules as well. I'll come to that at the end of the talk. And this has really been facilitated by those big interferometric arrays that we use now, such as ALMA. So we have around 29 unique molecules now detected in protoplanetary disks that we can really start to compare also with what we see in the COMET record as well. And that's not including isotopologs. So we do see lots of molecules that have carbon-13 substituted or 15 nitrogen substituted, 18 oxygen, for example. And for those of you interested in isotopic studies, we do actually see some of these isotopologs in disks as well. So that's the molecular inventory that we currently have. But these molecules are not just telling us what the disk is made out of, it's also giving us a huge amount of information about the properties of the disks themselves. So, and I'll give you a few different examples of how we do that. For example, we can measure the disk mass. We want to know the mass reservoir we have for forming a planetary system. We can use carbon monoxide for that. We can use multiple lines of a single molecule to dig out the temperature because different lines will have different energy levels populated, and we can do kind of a retrieval of that and work out what temperature the gas is emitting at. We can use heavy molecules to work out the density of the gas. We can use high resolution, well-resolved lines to work out how the gas is moving. So we can look for things like shocks, or we're starting to even try to find protoplanets through these kinematic studies. We can study how molecules are being dissociated by the central star by looking at small radicals like CN and C2H. We can use cations to study the ionization fraction of the disk. This is important for thinking about how, if there's magnetic fields are playing a role in driving disk accretion and evolution, then it will be those cations that will be better coupled to the magnetic fields in the neutral. So we can use these to look at the ionization fraction. We also have deuteration. At low temperatures, molecules prefer to host deuterium rather than hydrogen. So if you see enhanced ratios of a deuterated form of a molecule versus the hydrogenated form, that tells you something about the provenance of that molecule. It must have formed in a lower temperature environment. We can probe things like turbulence, how well the disk is mixing, by looking at the shapes of line profiles. We can look at fractionation, as I've talked about. We can actually look at snow lines and map snow lines as well, and I'll talk a little bit about that. And finally, because we know these complex organic molecules likely form on the surfaces of dust grains, then we can look at kind of the ice chemistry that's ongoing by looking at these complex organic molecules. So a few little case studies just to go through. So what is the gas mass in protoplanetary disks? So what you're looking at here is the density structure of a disk in the colour map. So we're going from 10 to the 4 particles per centimetre cubed to about 10 to the 10. So you see the densest region of the disk is towards the star, and it gets more diffuse as you move away from the midplane and towards the outer disk. So this is the radius of the disk and the height of the disk. So we're looking at a quadrant, if you like, of the disk. So it's 99% by mass gas and 1% by mass dust globally. But the gas is, of course, about 90% hydrogen, 10% helium, and only about 0.1% carbon monoxide. We can't see molecular hydrogen very well. It's only excited in the very inner regions where it's hot. It's got some infrared lines that we can use. It's not excited out here where the bulk of the mass of the disk is. Helium we can't see at all, really, unless it's, again, coming from the very inner region. So we need to use these, again, sub-millimeter tracers such as CO. But the CO isn't homogeneously distributed through the disk because of this chemical structure that I told you about. So in the midplane, below about 20 Kelvin, it'll be frozen out on the surfaces of dust grains. In the disk atmosphere and in the outer regions of the disk, it's going to be dissociated by that radiation coming from the star. So the CO is only really in the gas phase in this kind of shaded region here. So it's not really tracing the bulk of the disk. And this is quite tricky then. So a fundamental property that we want to measure, which is the mass reservoir of a disk, is actually really, really tricky to do. So a lot of people have done a lot of work actually coming up with diagnostics of this by running forward models. So taking disks of various masses, as you see here in the colour. So each of these points, so these are the higher mass disks and these are the lower mass disks. Running forward models and predicting the line strength. So here you can see the 13CO 3:2 line on the x-axis and the C18O 3:2 line on the y-axis. So predicting the strength of emission we would expect for those two transitions based on the disk mass. And you can see here, we cannot use the main isotopolog because it's optically thick. We don't see all the way through to the disk. We have to use the rarer isotopologs as well. So you see here these diagnostics, and then you see overlaid on those are actual observations. So you see down here we have lots of upper limits, and then you see here some results of observations. So if we make these measurements, then we can use these diagnostics to say, this must have a disk mass of about 3 times 10 to the minus 3 solar masses. And then the difference between these two plots is just on this right-hand plot is an extra a level of chemical complexity is included in here where we have isotope selective fractionation and the photodissociation of those isotopologs. So these diagnostics have been used in large surveys, and that's one of the results of a survey here. So this is an ALMA survey of the Lupus star forming region, and what you see on the top, this is the dust mass gotten from the continuum, and then the only ordering here on the y-axis is each of these is a source, and then the sources are just ordered by increasing dust mass. And then on the bottom we see the gas mass here on the y-axis, and again each of these points corresponds to a particular dust mass in the top plot. And the first thing you'll notice here is there's no clear trend. So you see this clear trend because we've ordered the data that way in the dust mass, but there's no corresponding trend in the gas mass. So there's lots of different dust to gas mass ratios measured here. The main thing to point out here is this kind of line that I've put in the plot. This is the minimum mass solar nebula. So this is the minimum amount of mass needed in the disk around our young sun in order to form the planets in our solar system. And only the very, very highest mass disks even approach this mass. So it seems that disks that we measure, or at least use these diagnostics to measure the dust and gas mass, either these disks have very low gas to dust mass ratios, so our conversion factors aren't working, or the CO to hydrogen abundance ratio is not the canonical value of that 0.1% or 10 to the minus 4. And we see this systematically not only just in Lupus, but also in other star-forming regions like Chameleon 1 and also Upper SCO. So really, the survey so far suggests that the disks that we're looking at don't have enough mass to build a solar system. And this is a bit of a problem, right? Because we know planets form around stars, so we expect them to form in those disks, but from those disks we don't see enough mass to actually form those planets. So there's a little bit of a missing gap of information. Part of the puzzle actually comes from chemistry, and another key output from Herschel is it was able to see emission from these small hydrides such as hydrogen deuteride. So here you see a spectrum of the disk around TW Hydra, which is our closest protoplanetary disk to us, so it's very, very well studied. HD is a very good tracer of mass because it's actually not sensitive to chemistry. It's got homogeneous distribution, it's not frozen out, and it's not well dissociated as well. HD and H2 can self-shield themselves against dissociation. So it's got a very constant fraction with respect to H2 across the whole of the disk, unlike CO. But we only had Herschel for that little bit of time, and Herschel also only gave us spectrally resolved lines. We don't have spatially resolved information, but we have these very strong, nice transitions of the J equals 1 to 0 and J equals 2 to 1 transition, rotational transitions. And using a combination of models to infer the gas temperature and work out where the emitting surface of the HD was coming from, this work was able to infer that TW Hydra had a disk mass around 0.05 solar masses, which is well above the minimum mass solar nebula, and it has more than enough gas mass to form the planets in our solar system. So this is kind of part of the puzzle, and this is where chemistry is quite important. So these higher disk masses we measure from HD observations actually tell us that it's low CO to H2 ratios that are responsible for the low disk masses we've measured before. And then a big question that comes from that is what has happened to the CO? How have we gone from the canonical value of 10 to the minus 4 in the interstellar medium to a value that's probably 2 orders of magnitude less than that in the disk? And I'll tell you a little bit about that in a bit. So the other features that we want to look for in protoplanetary disks are also these positions of snow lines, because as I told you, they create very strong compositional gradients in the disk midplane that's important for setting the composition of the atmospheres of planets, but also the composition of icy bodies like comets as well. So here you have our solar system. The planets are to scale size-wise, but not to scale distance-wise from the sun. And overlaid on here you have a little cartoon, and we think that the water snow line, which discriminates between bare dust grains and water-rich dust grains here, lay probably around about in between the orbit of Mars and Jupiter, because we think that the snow line plays an important role for helping to amass the material needed for building the cores of these giant planets, Jupiter and Saturn. But the water snow line sits very, very close to the star, so of the order, between 2 and 3 astronomical units around a sun-like star, for example. And that's very difficult for us to resolve actually with molecular lines. But another snow line that's quite important, which really tells us where all the heavy elements are frozen out, is the CO snow line, and that is actually accessible with current observations, because we think the CO snow line in the solar system probably lay out beyond the orbit of the ice giants Uranus and Neptune, so 52, maybe 100 AU or so. So we can actually start to look for these snow lines in disks, and this is some really nice early ALMA work exploiting astrochemistry. So exploiting the fact that we know the chemical relations between different species to infer the positions of these snow lines. So what you're looking at here, so this is TW Hydra that you've met before. This is the closest protoplanetary disk to us. It's our nearest neighbour, if you like. And you're looking at emission from the molecule N2H+, which I've also introduced you to before as well. This is basically just protonated molecular nitrogen, okay? Same nitrogen that's in our atmosphere. And then you're looking on the right at IM Loop. That's a disk that's a bit further away from us. It's a bit more massive. So you see the scale bar here. This is 50 AU, whereas here this is 150 AU. And this is looking at a deuterated molecule DCO+, which is CO that's been got a deuteron attached. And you can see that the N2H+ emission is sitting in a ring, and the DCO+ emission is actually sitting in 2 rings, which is also very interesting. So why are these tracing the CO snow line? So the dotted lines here is where we've inferred the CO snow line to lie. And the reason that the N2H+ is lighting up beyond the CO snow line is because the reaction to form N2H+ is this one. So we take molecular nitrogen, it reacts with H3+, that pulls away the proton to form N2H+. But if you have CO in the gas phase, that has a higher proton affinity, so that likes protons more than N2 does. So that happily steals away the proton from N2H+ to form HCO+ and gives you back N2. So you see N2H+ lighting up in emission beyond the region where CO has frozen out onto the dust grain. So the CO is depleted, the N2H+ lights up. So internal to this, CO is mainly in the gas phase. So we use another tracer to infer a very important kind of property of the mid-plane chemistry. And then on the other side, we see the CO snow line is being traced, but kind of in the negative sense. So here we have H2D+ formed through HD, which you've met, again reacting with H3+. This acts as like a proton or a deuteron donor. So if you have CO in the gas phase, that reacts with H2D+, steals away the D+, to form DCO+, which you see here. So where you see DCO+ lighting up is where CO has come back into the gas phase to allow this reaction to happen. So CO is actually frozen out in between these 2 rings, where CO is frozen out beyond this ring. And the really interesting reason why we have 2 CO snow lines in this disk is because we think that in the very outer regions of this quite large disk, it's being warmed by the enhanced UV radiation. So it's got IM Loop sits in a region of enhanced kind of interstellar radiation. Those dust grains are being warmed, and that CO is being lifted back off the dust grains in the very outer regions. So already you see that you may not just have only one snow line in a disk, you may have multiple snow lines, and that's going to affect the abundances of your ices that are forming comets away out here in the outer disk. So I'm a little wary of time, so I'm going to skip forward a little bit, and I'm going to move on, I think, to talk about molecules and disks at high resolution. Okay. If you're interested in the bit I've skipped over, just give me a shout at coffee or at lunch. I was basically talking about some of those other molecular diagnostics we can use in disks. But this is the exciting bit. This is the bit I think you're interested in. So this is a nice image of the ALMA telescope, the Atacama Large Millimeter Submillimeter Array. And this has really been the machine that we've been using to really map the molecular emission coming across those protoplanetary disks that are very, very small objects on the sky. And there's been a few really beautiful results coming out of this. So I want to show you this result here, which is done by another team led by Arcetri in Italy. So this is now molecular emission coming at 0.1 arcsecond resolution, and this is towards a young class 1 object. So this is an object that still has its envelope and is still forming jets and outflows, so DG tau B. And this is one of the highest resolution kind of data sets that we had recently. So what you're looking at here, this is the CO emission, this is formaldehyde, this is CS, small sulfur containing radical, and this is CN, the CN radical. On the top, you're seeing the integrated emission, so the brightness of the emission in those molecular lines. On the bottom, you're seeing the kinematics of the emission. So blue means blue shifted, and yellowy red means red shifted. So we can look at the shifting and Doppler shifting of the molecular lines to infer the movement of the gas. And in the CO, you see this beautiful outflow that's been generated, and you also see hints of the disk down here. You can see the formaldehyde seems to be very well tracing the disk, whereas the CS and the CN is more tracing kind of the surrounding envelope. So already these different molecular traces are tracing different components in this quite complex object. If we look at the kinematics, again, we can see this beautiful outflow. I mean, we don't often get straight lines in space, but this is a very straight line. So this beautiful outflow. We can see this quite complex protoplanetary disk. We can also see streamers that seem to be feeding the disk from the surrounding envelope. The formaldehyde, the small organic molecule, is very well tracing the disk. And then the radicals, CS and CN, are more tracing that infall coming from that surrounding envelope. So, you know, we always had cartoons of these objects that looked a little bit like this, but really we were able to then really resolve using, you know, 10 AU resolution, really start to resolve all of these structures that we imagine happened. So we see disks, we see envelope, we see evidence of infall, and we see evidence also of outflow. So really powerful tracers. So we've been looking at our nearest neighbour, TW Hydra, in these very high resolution images as well. So this is a nice paper that I was part of, led by Hideko Nomura. So this is a 2 CO isotopologues, 13 carbon, 13 CO and C18O. And again, these two radicals, similar to the previous plots of CS and CN. And the first thing you'll notice, so this is the size of the beam. This tells you the resolution of the image that you're looking at. And the star is in the centre here. So you can see TW Hydra is nearly face on. You can see very clearly that the emission is not homogeneous across the disk. It's not that you have this nice gradient of emission across the disk. So the disk is not smooth. There's a lot of structure in there that's creating kind of these very strong radial profiles and molecular emission. You can see the CN is located in a ring, and you've got like an inner component here and then a ring and a more diffuse ring. You can see in the CS it's slightly different, so it's kind of overlaps a little bit here, but you've also got this weaker emission as well. In the CO you've got this very strong component and then this very weak component. And we're still trying to understand why we see these disks aren't smooth. We're still trying to understand why we see this quite complex morphology. So based on these kind of very high resolution observations, I was part of a team called MAPS, or Molecules with ALMA on Planet Forming Scales, that wanted to do very high resolution imaging of multiple protoplanetary disks in multiple molecular tracers. And this is quite a complex schematic, but it's very similar to the one that I showed you at the start of the talk. And the purpose of this large program, which was also kind of titled The Chemistry of Planet Formation, we wanted to think about what the dust and the chemistry were doing and how they were linked together. So you remember planets carve gaps and create dust traps. We wanted to look at what the organic reservoirs are, especially of carbon, nitrogen, oxygen and sulfur, and look at the deuterium ratios. We wanted to actually test this theory that we have this vertical stratification in molecular structure of the disk. And finally, we wanted to look at ionization and dynamical disk processes. So we had very high resolution spectra that allows us to do those kinematic studies as well. So these are the 5 sources that we targeted in that study. So we have IM-LIP, which you've met before. That was the DCO plus source with the 2 rings of DCO plus. And we're going from younger, lower mass sources up to older, higher mass sources from IM-LIP, GM Aurigae, AS209, 163 and 480. And what you're looking at here is the spatially resolved dust emissions. This is the thermal emission coming from dust grains. And you can see all of these disks have substructure in their dust. They all mainly have rings. And the reason why some of these rings are kind of ellipses is because the disk is inclined to the line of sight. The ring structure in the dust is different in all of the disks. AS209 has this beautiful ring in the outer disk. IM-LIP is an interesting source because it also has a spiral in the dust as well. So we chose these sources because they had different styles of dust substructure, and we're also probing to some extent a different mass and age range as well. And this is basically the overview of all of the observations that we have. So the 5 rows here, the 5 protoplanetary disks, and then each column is a different molecular tracer and a different molecular line as well. And you can see that all these disks look completely different. So they look, if you take an individual disk, they look different in all the molecular lines. And if you take a molecular line in each disk, again, they actually look very different. So here we have, in this disk 163, this emission is quite broad and goes across all of the disk, whereas here in MWC480, it's very compact. So we don't see the same chemical substructure in any of these disks. They're all incredibly unique. And we're still really trying to understand the reason for this. One of the papers that we produced as part of MAPS was kind of trying to associate. So these are the lines that we targeted. This is a very busy plot. If you're interested in it, I can go over it with you in more detail. The different colours are different groups of species. So the yellow here is the cyanides, the blue are the oxygen-bearing species, the purple are the hydrocarbons, and the red are the CO. And then overlaid in the background, so these are the positions of the rings and gaps that we see in the molecules. And then on the background, we have the rings and gaps that we see in the dust. And we basically see very little correlation, neither between, sometimes within a family of species, you know, we do see some correlation, but very often we can see molecular rings well beyond where the dust is sitting. In some disks we see just compact emission like MWC480 and very little in the outer disk. But even doing a statistical analysis of this, we don't see any correlation between where the dust is bright and where the molecular lines are bright, nor where one particular molecule is bright and another one is bright. So we found more than 200 chemical substructures, really wide diversity of morphologies, and we also see chemical substructure in rings. So again, no smooth gradients in the inner disk. There's really rings of composition, also found within 50 AU, which is the region that we're interested in for planet formation. And I have a PhD student that's going to start to answer some of these questions, hopefully, with forward modelling. So let's go back to, we're here to talk about astrobiology. So I'm going to come back again and talk more about complex organic molecules, okay? Because that might be, again, more what we're interested in. So molecules and disks at high sensitivity. We need really high sensitivity to see the very weak line emission coming from these very large molecules. The larger the molecule, the more complex the spectra, but also the lower the abundance. So you're really looking at very weak lines. And this is really where ALMA, as you can see in the background, has been transformational. So this is our schematic. This is our molecular cloud, our protostar that's growing through an accretion disk from a collapsing envelope through to our protoplanetary disk, and then finally our planetary system. We have a little comet here in our planetary system as well. So we know from actually quite a long time, mainly single dish observations, if we look at molecular clouds, we look at protostellar envelopes, and we look at comets, we actually see that these environments are quite rich in these complex organic molecules. But there's still a big question mark, or there has been still a big question mark, about whether these same species we see in these environments are also present in the protoplanetary disk. And a lot of people have been looking at this. So this is a nice example. This is a forming multiple protostellar system called IRAS 16293. Where you have source A here, which is an edge-on disk, and source B here, which we think is a face-on disk, but it's very highly optically thick because it's surrounded still by an envelope. And there was a very, very high resolution unbiased line, unbiased spectral line survey taken towards source B here, which is one of the chemically richest, I think, protostars that we know of. And from this spectral line, observations, and this work led by Maria Drozdowska. So she looked at the abundance in this source, IRAS 16293, of a lot of these complex organic molecules, and she compared them with what were measured in Comet 67P, which is the comet that the Rosetta mission visited. So we've got very, very nice observations of that we can compare with this protostar. And the shaded region here is kind of the one-to-one correspondence. And what Maria found just in this comparison of what we see in this protostar versus what we see in the comet, nearly a one-to-one or almost a one-to-one correspondence if we compare with the abundance of methanol in both sources. So, you know, this is the protostellar envelope versus the comet, and we really see that there's a lot of similarities, at least in one comet, right, that where we have this quality of data. So it really does look like that these have similar abundances, which already hints at the fact that some of the stuff we make early is preserved to some extent in the cometry record in the disk. So let's now look at those more class 2 discs. So by far the most common observed large complex organic we see are actually these cyanides. So methyl cyanide and cyanoacetylene, CH3CM, which we also see in comets as well. And this is some results that you see here. So this is 163296, V406 SAG, MWC480. You've met these 2 discs already in the MAPS survey, which I'll also show you. And then this is the methyl cyanide emission in blue, and this is the CH3 N emission, cyanoacetylene emission in red. And then you can see that again, we had hints here, this is the dust emission as well. So I think the main thing that we found from these early surveys with ALMA is that the complex organics are sitting well within the dust disk. They don't seem to be very, they don't seem to be as spatially extended as some of the simpler molecules. They really seem to be tracing the dust, which I think is giving us a hint that the dust and the complex organics are talking to each other in some way. And then with MAPS, we actually went back and did these observations a little bit more deeper. So here's our 5 sources again with our MAPS large program. Here's cyanoacetylene, methyl cyanide, and another hydrocarbon, C3H2 cyclopropionylidene. And you can see that, again, this really confirms what we know. The emission from these larger hydrocarbons is really coming from well within the spatial extent of the dust disk. If I were to overlay the CO on top of this, the CO would be 2, 3, 4 times larger than the dust disk. So these large molecules seem to be really well associated with where the dust is actually abundant. So we took these observations, especially for the methyl cyanide and the cyanoacetylene, and we computed their ratios with respect to HCN, and we compared them with what we knew already from the cometary record. So in yellow, you have the cometary record here on the top. We have the 4 disks where we well detect these molecules, and then we have the radius on the x-axis as well. And there's kind of 2 take-home points from this plot. So our observations are in blue, and the comets are in yellow. So first of all, we see a large diversity in comets. Okay, no one comet looks the same as another comet. But actually, in our observations, we're reproducing that kind of diversity because we have these compositional gradients. So we actually see the range that we see in comets also within an individual disk, which I think is interesting for the solar system. And also we have really good overlap. So up here we have some larger error bars. So it may be that this disk is a little bit more rich in HC3N than comets. But certainly we have a lot of overlap between what we see in comets and what we're seeing in disks. So I think that this is again, really good concrete evidence. So we have some degree of inheritance from earlier stages. So what about oxygen-bearing complex organic molecules? Because those are nitriles. Well, actually, this has been quite difficult to do. So they've actually remained elusive until 2021. We only had methanol and formic acid, and only towards TW Hydra. This is the dust emission from TW Hydra here. And we also only had spatially unresolved detections. So these are spectral detections. So this is the detection of methanol in TW Hydra. So this is the work I led a few years ago, and formic acid in TW Hydra led by Cécile Favre in 2018. But actually, we're starting to pick up methanol more and more. So this is a work led by Alice Booth, who was my PhD student and is now in Leiden. So we got the serendipitous detection of methanol in actually a Herbig disk, HD 100546. And this disk is warm. This disk is around an A-type star, which is at 10,000 Kelvin. We would not expect to find methanol in this disk or forming in this disk because we don't actually have any CO freeze out. So remember in that video I showed you that methanol forms from hydrogenation of CO ice. So if we don't have any CO ice, how can we then make methanol to reach kind of this level of brightness and column density that we can see it? So we think that this is really pointing towards a very high degree of inheritance from the interstellar cloud. So the methanol that we're seeing has been inherited by the disk and has survived actually the disk evolution and formation process. And if we compare the methanol that we see in this warm Herbig disk with a cold Herbig disk, where we're not seeing the ices at all, which is 163, to TW Hydra, where we'd seen it before, then this is much more, it has much more methanol in it, relatively speaking, than TW Hydra. So we think that even these warm Herbig disks are now host to much more complex organic reservoirs than TW Hydra. So what we think is happening is a little cartoon here. So the disk is fed by ices that have not seen much processing, so the methanol has survived. That makes its way into the outer disk. That's frozen out on dust grains. Because of that radial drift that I talked to you about at the start, those dust grains move inwards to a warm region where those ices can sublimate, and then we see those ices in the gas phase. So we think that we're seeing a combination of inheritance, preservation, and then sublimation, again kind of preserving those molecules. So we think this is a very good indicator of a high degree of inheritance of ices by protoplanetary disks. So we're starting to see more and more of these objects. This is the IRS 48 ice trap. This is the millimeter dust. The CO this is where the star is. So the dust is all on one side. If we look at the complex organics in the SO2, that's all sitting on the same side of the disk as the millimeter dust. So we think this is an ice trap where we're seeing the sublimation of ices in that dust trap. And this is, again, coming back to those disk physics that I told you about. We think this dust trap has been coalesced by a forming planet, and then we're seeing strong vertical mixing, bringing those ices up to the upper layers of the disk where they're sublimating, and we can see them. And then the largest molecules detected to date are dimethyl ether and methyl formate. And again, this is an IRAS 48, so this is the dust emission, this is where the methanol is, this is the dimethyl ether, and this is the methyl formate. This was led by Sandra Brücken in Leiden, but we actually have follow-up data on this where we have loads and loads of molecular lines, so stay tuned for that. And I think that if we compare, again, this is taken from Sandra's work, if we compare the ratios that we have in IRS 48, which are the black stars here, they don't quite overlap with this protostar that we talked about, IRS 16293, nor with TW Hydra, nor with Comet 67P. So there's something interesting going on in IRS 48 that's reprocessing those ices. It's maybe a little different from what's going on in HD 100546. Okay. I flew through that bit, so if you want to know any more, come and see me at coffee. So what do we know about organic chemistry and solar systems? So at the moment we are resolving Snow-line positions. We're able to map those compositional gradients, those changes in C over O ratio in the midplane. We're now seeing a huge amount of chemical substructure. There's a lot of coupling between the disk physics and the dust and the chemistry that's leading to these radial gradients and structures in the emission and the composition. We're now seeing these complex organic molecules, allowing us to compare with what we know in the cometary record. And we're also now really getting onto size scales that really probe the composition of the planet forming region. And I think the main takeaway point from here is that planets and also planetary system objects like asteroids and comets are forming in really chemically diverse environments. It's not that these disks are homogeneously smooth in neither their physical nor chemical structure. Within an individual disk, we see a lot of substructure and a lot of deviations from kind of a smooth substructure. So this is something that I think is the main take-home point, is that disks are not smooth. There's a lot of complexity in there, and we might imagine that that creates lots of compositional gradients in the objects that we make. And I'll finish there, and I'm sorry for going a little over time. Thank you.